State and Seattle in particular. Okay, so in order for us to quantify ground shaking, we make recordings. Earthquakes happen, and we make recordings of the way the ground shakes. And the way the ground shakes is different at different places. Not only it's different because of the conditions that we have, it's also a function of how close you are, how the big earthquake, the size of the earthquake, and how big the earthquake is. And you get shaking that happens deep in the ground, in the bedrock. And then it travels, these seismic waves travel through this near surface material, which could be rock or soil. And this near surface material filter and amplifies this kind of ground shaking. It's very similar to a sound system that we have in our homes. And the degree of this modification of these seismic waves depends on what kind of subsurface conditions you have, obviously the level of shaking, and what is the frequency content of these incoming waves. So how do we develop this response spectrum? And response spectrum is basically the level of force in structures. So once we make these recordings, we do a mathematical integration of these recordings, and we do it for a single degree of freedom, simple damped oscillator. Basically is a spring and a dashpot, and then it has a damping value associated with it, and typically for structures is about 5%. So what happens is we solve the equation of motion, which is force is equal to mass times acceleration. And then what we do is we make this oscillator. We look at different stiffnesses of this oscillator. And the way to characterize this is either by the natural period of this oscillator, which the shorter periods are stiffer oscillators or stiffer structures, and the longer periods are more flexible and perhaps taller structures. And what we do is once we do this mathematical integration, we compute the maximum value of that response at a particular period or frequency. And then we plot it as one point on this portion of the plot that is on the right side. And then we do this for a whole bunch of periods or frequencies, and then we create this spectrum. In this case, in terms of acceleration, we can do velocities and we can do displacements as well. And generally speaking, rock type spectra tend to be richer in the shorter periods, and the soil spectra tend to be richer in the longer periods. And like I said, you pick a period and you hit this curve and you come to the left. This is basically the level of force in your structure. So that's what a response spectrum is, and that's the basis for seismic design. Now, as far as the entire United States is concerned, United States Geological Survey is the responsible agency to develop seismic maps, the way the ground shakes throughout the United States. And those maps basically form the basis for seismic codes. To the left is a set of maps in the ASCE 7 document that was published in 2010, hence ASCE 710. And the ASCE 7 document is a reference standard. So whatever ASCE 7 publishes becomes a reference for like International Building Code, and more than that, it could become International Building Code, then can become like state codes. California has its own code, probably Washington has it, same thing all over the United States. And then to the right is a set of maps that was prepared as part of the ASCE 716, which is the latest code, jurisdictional code right now. And as you can see, the Western United States are in warmer colors, obviously the greater level of ground shaking. And the differences between the two maps, there are some differences, but generally speaking, they are fairly similar. The Western US has the highest level of ground shaking from border of Mexico to Canada. Then we have regions in the East, one that you see in the kind of the Midwest in red color in kind of a circle, that's a New Madrid fault zone. And then one in Charlotte, South Carolina that experienced a large magnitude about 150 years ago. So there, as you can see, there are some differences, but not a heck of a lot, at least in these basic maps. And those maps that the USGS generates are for these reference rock conditions. But as I described before, soil, when you are in different kinds of sites, and we classify these sites, as you can see on the right side of this slide, from hard rock all the way to soft soil. And the degree to which that these reference values get modified are based on amplification factors that you go from the mapped values that are shown here in terms of the dark black curve here in solid black circles S sub S, which is a short period spectral value, and then 1 second, which is S1. And there are different types of factors that we use, a short period factor that is called F sub A. Then you modify this SS value to some value that is called SMS, which is for your site, using this FA value. And then you modify the 1 second value based on a different set of amplification factors called F sub V. And then you modify that. And then this green spectrum becomes your maximum considered spectrum, which is for very rare events, and you take 2/3 of that, which forms the basis for the design earthquake for buildings and structures. To give you an impression of how things have changed between 2010 and 2016, the set of these site coefficients for the short period, which is FA, is on the top table to the left. Bottom left is the set of coefficients for F sub V, and to the right are the same set of coefficients for the 2016 version of ASCE 7, and the numbers shown in red are the changes that we have had from 2010 to 2016. And you can see by and large, the numbers have somewhat increased in the short periods for stiff sile condition, like a C-class condition. And also, more importantly, they have also increased in the long periods, which is really important for taller structures. And the other important point here is that these tables, especially for the long period site coefficients, for site class D, which represents a stiff site condition, have increased, and they have an asterisk next to them. And the asterisk says that you have to do site-specific kind of determination of ground shaking at a particular site. Next. And some of the changes of these conditions is because you can see this spectrum, as I described earlier. You do a whole bunch of these types of analyses to come up with all of the values of this spectrum for different periods. But the code has only a 2-period kind of spectrum design basis. And really a 2-period spectrum does not capture the softer sites behavior. And that has been addressed by new provisions in Chapter 21 of ASCE 716. And to give you a flavor of what things will come, not in the immediate future, but in about maybe 5-6 years, this is the new version of the ASCE 7, which is ASCE 722, and I'm involved with that standard. There will be more site classes, and we will do away with this two-period spectral values. So it's going to be multi-periods and more site classes. As I mentioned, for basically stiff site conditions at the levels of shaking that we're going to be experiencing in the Western United States, Washington State, Oregon, California, site-specific is required because the mapped values, the provision is that for site classes D and E, which is stiff and soft conditions, if your 1 second spectral values, and these are the mapped values, are greater than 0.2 times the acceleration of gravity or 20% of gravity, which is pretty much the entire United States. It's shaded here in highlighted in yellow, and you can see everywhere that we are, we have to do site specific. Now, there are some exceptions that are in the provisions of ASCE 17 in chapter 11, section 4.8, that gives you some exceptions that you can take and not do site specific, but there is a penalty. There's basically a 50% penalty in terms of trying to take these exceptions as opposed to doing site specific. There are some other criteria with respect to ductility and the period of the structure. So this is kind of to determine whether or not you need to do site specific or not. It's kind of a little bit of an interaction between structural and geotechnical engineers. Next, please. So the way we develop site-specific, we go to chapter 21 of ASCE 7, and to develop the site-specific, we have to look at a very rare probabilistically developed spectrum for a return periods of 2,475 years, or 2% probability of exceedance in 50 years. And what does that mean? 50 years, generally speaking, is a life of a structure. Doesn't mean that you get to year 51, you can't use it, but that's how it has been looked at historically from a building code perspective. And 2% probability of exceedance, what it means is that in the probabilistic framework, we're going to capture 98% of the levels of ground shaking. So we have this about 2% that can be exceeded. So that's the definition of this level of probabilistic spectrum with the 2% 50 years translates itself into this 24-75-year return period. Or a deterministic spectrum, which is basically you have a site, you have a fault that can generate an earthquake, and that earthquake could be a magnitude 7, 8, whatever, the maximum that can be on that fault, and you're X kilometers away, say 10, 15, 20, whatever it is. So you do a very simplistic way of looking at it in a deterministic way, and the lower of the two you will take to develop this maximum considered spectral level. There are some other checks that you have to do. The deterministic cannot be smaller than a limit that the code provides. But the most important thing to note here is that the long period site class factor F sub V in the new provisions have significantly increased. For F sub V for site class D used to be a factor like 1.5. and now it has gone to a value of 2.5. And the reason for that is to capture issues with deep basins, because we know when we have a thick deposit of overburdened soil, that once the earthquakes happen, the longer period spectral values will be influenced by how deep this basin is. And in addition to these provisions, City of Seattle has its own basin depth provisions as well. And for site classes E, which is an F, which is special site classes, or soft site classes, the long period F sub V value has increased from a factor of 2.5 to 4. These increases are about a factor of 67%. So it's very significant increases that we have to deal with these days. And this gives you an impression of this deterministic lower limit that I was talking about, so that your deterministic values cannot be lower. For site classes D are shown in the blue curves. The solid blue is ASCE 716, which is the current code, and compare that to the previous version 710. You can see, which is shown in the dashed blue, you can see there is a significant difference in terms of longer period spectral values, which means much higher levels of force to be designed for. And similarly for site classes E, which is a soft site class, we go from what we used to have as the dashed red curve here to the solid red curve, and you can see in the longer periods is much greater spectral values. Now, so that was a kind of a big picture provisions in throughout the United States as far as ASCE 7 is concerned. Now we go to Pacific Northwest, and the main source here is the Juan de Fuca plate, which is a subducting or going under the North American plate, and this dipping under creates earthquakes when the rocks go past each other. And then this is the subduction source, and we have two kind of different types of subduction earthquakes. One that are in what is called the intraslab, which is the shallower earthquakes, and then there are these interfaces which are much deeper earthquakes. And based on recorded data, we know that these two types of earthquakes are different from each other. So the way we estimate ground shaking for these particular types of earthquakes are a little different from each other. And so we look at them specifically on their own terms. And then we also, in the Seattle area, we have the Seattle fault, which is a shallow crustal type earthquakes. And those are kind of the levels of shaking, and the way the ground shakes is also different for those for the crustal or shallower earthquakes. So we quantify all of that when we do site-specific determination of ground shaking for the Pacific Northwest. City of Seattle, also a director's rule that came out in 2018. As I was talking to you about the basin depth effects, that ASCE 7 is now kind of quantifying it and its significant increases, but also City of Seattle, because of the depth of basin that is particular to the Seattle region, has its own amplification for these longer periods. Whenever we do work in obviously Seattle, we have to kind of go and include these provisions as well in our quantification of site-specific values. So as I was saying, these basin depth effects, and this is for a site in Redmond that we recently did site-specific evaluations. These different types of earthquake, like the interface and the intraslab and the crustal, they have different types of basin depth amplifications, and the values that are shown in the city of Seattle documentation. It's about a value on the order of about 2 for periods. So you have to increase your values by a factor of 2 for periods longer than, say, around 2 seconds or so. But when we do site-specific, we look at the contribution of these different types of earthquakes to the overall hazard that we are computing. And we use a weighted average of these different kind of basin depth effects. And in this case, you can see it goes for shorter periods. There is no amplification. It amplifies the motions as you go to about a period of 1 second on the order of about 1.5 times. And then maybe for this particular site, we got to a value of about something like 1.8 for periods longer than 2 seconds. So we include these kinds of quantification in the Washington, Seattle area. Similarly, we did another site in Seattle, and the basin depth effects are a little bit different because of where the site is, how much of a particular kind of an earthquake contributes to the hazard. So the basin depth effects are different depending where you are. So just to give you an impression of how these, as I said, USGS develops these maps. These are for 3 areas, 3 site classes. We put in San Francisco because I'm from San Francisco. So, and obviously Seattle and Redmond as well. This is for site class B, which is a soft rock condition. ASCE 710 is shown in the black bar charts, and the spectral accelerations are on the y-axis, and the red is ASCE 716. You can see by and large for rock has decreased somewhat. Then we go to this site class C, which is a very stiff soil conditions. Now we are seeing that actually the values for spectral values at 0.2 of a second actually have gone up pretty much everywhere: San Francisco, Seattle, Redmond. And then we get to site classes D. It's kind of there is not much increase in San Francisco, and a slight bit increase in Seattle and Redmond. So that was for short periods. If we go to the longer periods, we see essentially the same patterns, but we also are seeing a little higher level of amplification for 1 second values for the stiffer site conditions. So this slide is intended to give you an impression of if one were to take those exceptions and not do site-specific. This is for a site in Redmond, as I previously mentioned. Our site-specific design earthquake is shown in the blue line. So if we chose to do site-specific, that's the numbers that we would get. And if we chose to take the exceptions, but also take the penalties that associated with not doing it, the curve is shown in red. And as you can see, there is for sure for this site value to do site-specific, because let's say if you have say a period of 1.5 seconds for your structure, you have to design it for a acceleration value of almost 3/4 G versus a value of 0.5. So that's a good is that almost 30% increase or so. There is for sure value in terms of doing site-specific for whatever structure you want to look at. Next. Kind of give you a quick conclusion of what we've discussed. The mapped base values, which are for this reference rock, have generally decreased. And that's because the factors that now we are using for site class B is a little smaller than before, and it's more appropriate. We know that the factors for other site classes, C and D, these FA and FV values, they have increased for site classes C and D, large levels of shaking. This is not a completely correct statement. We don't even have factors for classes B. We have to do site specific for site classes. So if we do site specific, at least in the one example I showed, there is for sure an increased value. And then for soft, there is going to be a big because of these minimum checks that I told you that the values of these minimum checks have increased by almost a factor of 67% or so. So with that, my portion is done, and I turn it over. Oh, well, actually, one last thing. This is a recording. You all have heard about liquefaction, what it means, et cetera, but this is a recording that I don't believe we can hear the person who is recording it. And this happened in the Tohoku earthquake in Japan, which you probably heard with the Fukushima event and everything that happened with that earthquake and all the devastation. And by the way, we got tsunamis in coastal California, which was about only 6,000 miles away, and from the other side of the Pacific, the tsunami traveled from this earthquake. And this little video is at Chiba City, which is this area just outside of Tokyo. And just for reference, this area is about 200 kilometers away from the epicenter of this earthquake. But this earthquake was a magnitude 9.2 subduction type earthquake. And let's see what happens. So like I said, unfortunately, he does a great job, this guy Brent Cui, describing everything. But this is as the earthquake is happening. The ground is separating, and you can see movements, and then it just keeps going. And now ground keeps, there are going to be cracks in the ground, and then he pans over. For now, it looks okay, but as you can see, now this is liquefaction in action. The soil has liquefied, and you get this ejecta, which is this basically a reverse gradient, because there's higher pressures lower in the ground, and with the water, and then it liquefies the soil and brings it up. And you can see it here as well. On the edge here, the ground has liquefied and continues to liquefy. It brings up soil with it, basically is saturated. Loose sand is the worst kind of conditions that you can have when earthquakes happen. And now that whole area has turned into a little lake. And I don't know, we're going a little slow here, but you can see the ground is moving back and forth, is oscillating. Now you have significant cracks in the ground. So when you hear liquefaction, it is real. And this is on YouTube. You can download it if you're interested. And also, when I was talking about tsunami, it's the tsunami that was the result of the Tohoku earthquake basically destroyed Crescent City Harbor, which is border of Oregon and California. And this was from an earthquake that happened 6,000 miles away. So all these seismic hazards are real, and they will do bad things. And with that, I turned it over to Patrick. Thank you.
Okay, well, thanks, Ramin. Again, my name is Patrick Lindblom with DCI Engineers, and I'll be explaining what we do on the building side or the design side once we establish the seismic hazard that our buildings or our sites are sitting in. But first, a quick overview of DCI Engineers. We are a structural design company. We have got 13 offices, mainly on the West Coast, so we are very familiar with the seismic hazards working along the Pacific Rim. But you can see we are also expanding out eastward into Colorado, Texas, and Montana as well. We're licensed in all 50 states, over 300 support staff, so we can help you with any of your structural or civil engineering needs. Okay, so touching really quick again on the codes that we are looking at, the 2018 International Building Code, as Ramin mentioned, this is the reference standard, but is typically adopted almost verbatim into every state or every local jurisdiction with some minor tweaks here or there. This International Building Code points to the ASCE 7, which gives all the building loads that we have to design for and support. And the 2016 edition is the latest published version of that standard. Okay, so in this ASCE 716, a lot of the seismic changes, which we're going to be seeing, are due to a couple of things, which Ramin has already touched on. Specifically, the site coefficients are changing and the requirements for doing a site-specific evaluation. But on the building analysis side, there is one more provision which has to deal with analysis scaling, and I'll describe that a little bit more in the next couple of slides. But those three factors are really what's going to be pushing forward and showing a large increase in seismic loads for certain locations in the next code cycle. So again, here's a couple of slightly modified. These aren't the exact response spectra that Ramin produces, but these are closely related to those. And what they're showing is, again, the relative difference between the ASCE 710 version and the ASCE 716 version. And I am zeroing in on site classes C and D, which are primarily the site locations or the site profiles that we're seeing in the Seattle region. So as you look at these two plots, what I'd like you to think of are shorter buildings on the left, and as you progress to the right, getting progressively taller with your potential projects. So starting on the left in site class C, we're going to see a slight increase, about a 23% increase in the site coefficients for shorter buildings. And as you get slightly taller, that difference tapers off and gets pretty minimal. Whereas if you look at the site class D plot on the right-hand side, it starts pretty minimal, the difference between ASCE 710 and 16, and then you can see there's a wide gap that opens up as you get slightly taller in your buildings, and it tapers off again. So that wide range where we're getting about a 67% increase in our loads, that's the spot where we're going to really have to look at the challenges to designing structural lateral systems for that type of project. Okay, so the height of the building, that period or the height of the building really plays into how the building responds to a seismic event. So shorter buildings, they don't have much flexibility. So when a seismic event does occur, they basically are just holding on to the ground and they're along for the ride. So they have relatively high accelerations and high loads that we have to account for. Typically for projects, we have a fair amount of locations where we can put a lateral system in shorter buildings, so it's not too big of an issue. However, as you get taller, up to the 10 to 20 story range or the 40 story range, those buildings do have a lot more flexibility in them. They have a lot more flexibility overall and just ways to dissipate those seismic energies. So the loads go down and taper off overall. However, there is going to be still a big difference between the way a shorter building versus a taller building responds. So building dynamics, this is that third point that I mentioned, the analysis scaling that we have to do on the building side of things. We used to get a reduction in our seismic loads for doing a modal analysis. And a modal analysis is essentially taking our building, putting in all the lateral systems, all the walls, and shaking it and seeing what the stiffness of our building is and how it responds to the earthquake. Well, more recent studies are showing that that is a slightly unconservative approach, so we're having to increase the scaling that we do for that analysis. So there's about a 17% increase in loads right off the bat for that type of analysis that we're doing. So trying to boil this down and say, okay, what types of buildings or what types of locations are going to be most impacted by the change to the next code cycle. And what we're seeing is that tall buildings on softer soil sites, namely site classes D, E, and F, are really going to see that largest increase, that approximately 67% increase for the site coefficients and site-specific analyses. So those are the types of buildings that we really have to look out for. Buildings that are less than 80 feet are kind of going to fall into that shorter building range, and buildings that are over 240 feet tall are typically already doing a performance-based design and a site-specific analysis. So these code-based projects in the 80 to 240 foot range are probably the ones we're going to have to look out for the most. Okay, looking a little bit closer at the Seattle region, I mentioned that site classes C and D are kind of the breaking point. Going from C to D is a large increase in our lateral loads. So we wanted to get an idea about the neighborhoods in Seattle region where this is, a big question. So first off, on the north end, there's a lot of development going on in the university district these days with the upzoning and the increased height limits. So a lot of that area is going to be in a site class C. So for tall buildings in site class C, there's not too much of an increase from one code cycle to the next. Moving a little bit further south into the South Lake Union area, again, a lot of development going on there. However, this is a much softer soil type in that area closer to the south end of Lake Union. So these may be on the border between C, or a lot of those sites are in the site class D area. So we'll have to look at those pretty carefully. Moving further into downtown, a lot of those sites are typically in site class C, but it is pretty close to the borderline between C and D. So we, again, have to look at those sites very carefully and work with our geotechs to establish what site we're actually sitting on. And then moving further south, the Soto district, that's very soft soil down there. A lot of those sites are on reclaimed land. So those are typically going to be in the D, E, or F range, where a site-specific analysis is going to be required. Looking out east across the lake in Bellevue, pretty much everything is on site class C, so it's not as much of a concern, but we do want to point that out for potential projects moving forward. Okay, so we're highlighting the changes so far in the building code from one to the next. So what can we do about these? So first, as Ramin touched on pretty in depth, is the site-specific analysis. And I just want to mention that a site-specific analysis right now is not standard practice. Those only happen on about 20% of new projects. Typically what they'll do is go out, they'll take their site borings, do the shear wave analysis, and determine the site class from there. However, doing a site-specific analysis is a much more rigorous analysis on the geotechnical end, so that is an option that we'll have to determine upfront as to whether there is enough savings in terms of lateral loads to perform that analysis. Another approach that we have is to do a brute force approach, whereas adding more structure just to handle the increases in loads. If the increase in loads is minimal, then adding a little bit more structure may be the best approach. If it is not, or rather if there is a larger increase in loads, the other approach is to look at adding additional structural systems or more unique lateral systems, such as supplementary frames, or if the increase in load is really substantial, looking at base isolation or damping systems. And our fourth option is to put our buildings on a diet. So Ramin mentioned Newton's law of force equals mass times acceleration. So the accelerations, as we can see, are going up for certain building classes. If we can reduce the mass of our buildings, that directly affects the overall force that we're seeing. So that can mitigate some of the changes that we're seeing from one code cycle to the next. The image here is of a project we did in Texas, and we actually used a sloshing damper for this particular project to mitigate some of the wind accelerations. That also had the added benefit of also being used as a fire suppression system. So it's essentially a large swimming pool at the top of the building to slow down the motion of the building, but also being used as the backup water tank for fire events. Okay, so touching a little bit more on this site-specific analysis, as Ramin mentioned or alluded to, that they will go out and look at each specific location and do a 360-degree view of all the faults and how far away those faults are and how they could potentially impact that particular project. So, as I mentioned, this is not standard practice these days, but I do think this is going to become a lot more relevant or a lot more common with projects moving forward, particularly on the softer soil types. Okay, so as we started progressing through learning these code changes, we wanted to take some case studies for actual buildings that we had designed in the Seattle region and see, okay, if we started from scratch today, what would be the new base shear or the new seismic loads that we would have to design for. So we started with this particular project here, which is in Seattle. It's a concrete, cast-in-place concrete building. It was originally done in site class C, 160 feet tall, so it's going to fall into that taller building type of category. And in this site class C location, we're seeing the site coefficients increase the base shear by about 7%, which is pretty minimal. And then when we tacked on that added analysis scaling factor, which I mentioned just a little bit ago, the total difference is about a 26% change in load. So 26% is not a huge amount of load change. We could probably handle that with a typical framing system. So a brute force approach would likely work in this scenario. This is a floor plan of that same project. That is the lateral system that we eventually ended up with. And you can see that this is, again, a cast-in-place concrete shear wall system. So we took the same building. The second step of our study was to say, what if this had been located in a site class D location? So we did not do a site-specific analysis for this. We did this in-house prior to getting a hold of Langan, and we took that code exception and that code penalty that Ramin mentioned, and so that increased not only the site coefficients, but there was a 50% increase in the loads overall for doing that and taking that penalty, which is the 68%. And again, tacking on that additional analysis scaling, we end up with a 98% change in loads from one code cycle to the next. So this is a little bit alarming. You can see that if you just imagine putting 98% more lateral load into this lateral system, it's probably not going to work. We're going to have to add some sort of supplementary frame or some sort of additional walls to this floor layout. And you can imagine that that's going to have, you know, an overall impact on this project and the unit layouts, perhaps, or the perimeter system having to do some sort of additional frames. Okay, doing the same study for a different type of project. This is a pretty common podium type of project with 5 stories of cold form over a 4-story concrete podium. The concrete podium being 55 feet tall. This was located in a site class D location. So 55 feet, again, is kind of being on the shorter side of the building range. So you can see, again, the difference from one code cycle to the next is actually not very significant, even including that amplification factor of the analysis. So turning it backwards and saying, well, what if this had been located on a relatively stiffer site, a site class C location? You can see running through these numbers, again, we're seeing a little bit of an increase, or rather a noticeable increase, 21%, and with the analysis scaling about a 42% overall. But with this floor layout, again, I've highlighted where our lateral system actually ended up being. we can probably take care of the added load by thickening a wall here or there by an inch or two, or potentially making them longer by an inch or so. So we do have options depending on what sort of project that we are. Okay, so looking at some of the other options that we have if the load increase is really significant, and we do have to add structural systems for our lateral framing. Buckling restrained braces are becoming more relevant or becoming more common these days, especially with steel framed buildings. This is a project that we have over in Bellevue. It's in construction now, but we utilized exterior braced frames, or BRB frames, up through the height of the building. This particular project did not need to have a centralized core, and as we came down to the base structure, the lateral load in those braces was able to be transferred out to the basement walls. So we did not have to carry that lateral system down through the subgrade parking levels. So there was a lot of flexibility with parking layout, parking stalls, and drive aisles as we went down below grade. Another unique thing about this particular project was that typically the base structure will be concrete below grade. However, again, for this particular project, we decided to go with a steel framed substructure. And the reason for that was primarily due to the construction schedule. The additional shoring, the additional excavation depth for the increased floor to floor heights was taken into account. And overall, the driving factor here was the speed to market. The ownership team really wanted to be able to complete this project and get it occupied as soon as possible. So the steel framing system made the most sense overall for this project. Another really unique project that we have going on is this Grand Avenue Parcel Q in Los Angeles. These are two concrete framed building with a central core. And as the building goes up, it tapers to a typical floor plate. However, there are large extending wings as you go down the building. So in these wings, we had to utilize additional wing concrete walls and those BRB frames, which I mentioned. This also exceeded the height for a standard code-based building, so we had to go through a performance-based design. And as part of that performance-based design, we were able to use high-strength reinforcing in our concrete cores. Right now, the code limits us to 60 KSI reinforcing in our lateral systems. However, for this project, like I said, were able to convince the code jurisdictions that 80 KSI reinforcing met our seismic criteria. And we were able to reduce the reinforcing and reduce congestion in our concrete cores using that. A couple of other notable things about this particular project, being located in Los Angeles, they have softer aggregates down there. So the city of Los Angeles has started requiring modulus testing on the concrete mixes. So we did have to specify concrete testing to make sure that the stiffness matched the minimum or what we were expecting for both the lateral system and the slab, the flat work. We also implemented seismic instrumentation here, which is essentially accelerometers located throughout the height of the building so that when the earthquake does occur, we can get recordings of how those accelerometers throughout the height of the building respond and react to the ground motion. And we can directly compare that to our base estimates on the stiffness and the overall performance of the building. Okay, next slide, please. Okay, and the final portion that we mentioned was weight. Jen, are you able to go back one slide? Just touching on, again, the weight being a large factor in our final loads for the building. If we can reduce the weight of our framing systems, this can have a very noticeable impact. Typical framing structures for tall buildings right now are concrete and steel. However, timber framing is going to become a relevant or a building type that we should really investigate moving forward. And you can see the differences in weights. Timber framing is almost half the weight of concrete framing. So this can really have a dramatic impact on our overall loads that we have to design for. So digging a little bit more into that option of wood framing, the types of wood construction that we have available to us are type 3 typical stick frame or type 4 heavy timber up to 5 stories. And then you can take those same type of buildings and put them on a concrete podium to get up to an 85-foot height limit. Looking ahead on the next slide, the options that we have for type 4 construction are going to expand quite a bit. So just looking at this, the type 4 construction is being broken up into a class A, class B, or class C. And the corresponding height limits or story limits are listed here. And the difference between class A, B, and C are really just going to be how much gyp or how much covering over the structural wood members that we have. You can see class type 4, class C, completely uncovered, 100% uncovered. You can see we can go up to 10 stories, but realistically, we're going to be limited to that 85-foot limit. Class B, where we can go 80% covered or 20% uncovered, we do have the option to go up quite a bit taller than is currently allowed. Then correspondingly type A, 100% covered, we can get up to a 19-story building. And the type 1 is a performance-based approach, which I don't know that any projects currently proposed are going that route, but that is something that we could explore. So these are looking ahead at the next version of the IBC. This is already adopted in the state of Oregon. State of Washington is going to implement these height changes in the next code cycle coming up. So again, I mentioned we do have these options available to us, and we see a lot of potential for office type projects where office type typically want the open floor plate. So a post and beam type of framing system makes the most sense. We don't need to have the partition or the bearing walls in between units for a residential or a hotel type of project. But again, you can see the project on the left got nice wide open spaces. This is a project in Northern California that's completed now using the CLT or the mass timber approach. The image on the right is another office project using mass timber. This one's located here in Seattle. Okay, so moving away from new construction and asking the question about existing buildings. So what changes for existing buildings looking forward? The International Existing Building Code is also getting an update to their loads. If you go into the substantial alterations portion of the code, it says that we do have to meet current code criteria. So we would have to do the same types of analysis, and we will likely see increased loads for current standards. However, if we limit our gravity carrying elements or our lateral carrying elements to 5 and 10% of an increase, that's kind of our easy button. We don't have to do the substantial alterations in those scenarios. I've highlighted one particular project here, which was a substantial alteration. This is 8899 Beverly in Hollywood, California. And I want to point out the image on the lower right. You can see that this is the tallest building in this neighborhood. So the driver for this particular project was that the height limits for new construction have actually decreased in this neighborhood. So this particular building was grandfathered in. So the owner came in and thought, well, what if we tear this down and just build a new project? Well, the city jurisdiction said you will not be able to go up to the same 9 stories that you did with new construction. So instead, we went in and had to renovate the existing project. So looking at the next slide, we'll kind of walk through some of the alterations, the structural alterations that we had to do to meet current standards. First of all was the gravity system. This was built in the 1960s as a cast-in-place concrete structure, and all of the concrete columns did not meet current standards for seismic detailing in their columns. So we looked at a couple of options. Number one being adding 6 inches of shell around each column in which we could encase the reinforcing to meet the special seismic detailing. We also looked at potentially using fiber wrap on all the columns, but that ended up being cost prohibitive, and ultimately using 6 inches of shell or wrap on each of the columns made more sense for the project overall. Then the lateral system, it had originally been a concrete moment frame system, was not meeting current standards as well for seismic detailing in those moment frame elements. So we had to infill 2 bays in each direction with a concrete shear wall, and you can see the added reinforcing and the boundary element detailing that we had to implement within the building itself. And then the last piece, which was really an undertaking, was the foundation. Again, foundation was not meeting current standards. It had originally been a pile supported building with caps underneath the columns and underneath the moment frames, not meeting today's standards. So they had to go in and excavate underneath the existing building and fill in a 6-foot thick mat foundation under the entire in-service project. So this was a huge undertaking, and it only made sense, again, as I mentioned, for this particular building, this particular location. The owner was really driven to keep that 9-story structure and be able to charge, you know, the premium rates for those penthouse units. Okay, and the last component, looking at non-structural components, they are seeing an increase overall of about 20% due to the seismic coefficients increasing from one code cycle to the next. This will likely not come up too often, maybe just brace in direction for things like kitchen hoods, hanging kitchen hoods, or operable partitions or secondary framing. Okay, so looking at when these are actually going to be enacted. This had originally been scheduled for adoption on July 1st of 2020. Then the pandemic came along and the state code officials pushed that back to November 1st. I think that's actually the date that got sent out in the email notification for this meeting. Since that time, back in June, the code officials got together and pushed it back further to February 1 of 2021. So that is when City of Seattle and State of Washington are going to move into this 2018 code cycle. So we do still have a couple of months if there are any projects that are underway that could get fast-tracked and submitted before February 1, they could be vested in the previous code cycle. So what exactly do jurisdictions require for vesting in the previous code cycles? Looking at City of Seattle, anything within the City of Seattle jurisdiction, they are looking for a full building structural permit, which includes both below grade foundation and the tower as well. So structural package has to be complete for both the foundation and the tower to submit for that February 1 deadline to be vested in the previous code cycle. City of Bellevue is slightly different in that they are requiring only a below grade permit, but this has to include all of the associated trades, including mechanical, architectural, all the trades by February 1. The tower can be submitted at a later date. However, the up to grade and below foundation portions have to be fully submitted. State of Oregon and State of California have already adopted the 2018 version of the IBC, so any projects in those locations should already be looking at that version of the code. Okay, and that is going to wrap up my portion of the presentation. Again, I want to really thank everyone for joining us this morning and open things up to questions.
I would assume that the folks who are left do not have other commitments because we've lost a few because we did go over a little bit. So I'm just going to allow any questions to come forward to be asked and leave time for that. Anyone have something? Let's see. I don't. Oh, Bill has a question. Go ahead, Bill.
Just a quick one. Obviously, there's a change in the codes, and depending on what you're building and where you're located, it's going to be a little bit more stringent on the design and therefore the cost. So then we're going to go through another code cycle in another 3 years or so. Is this going to be the trend, where it's just going to be becoming more and more strict, or are we good on codes for a while as far as how much they've changed?
I'll take at least the ground motion side of that question. this cycle, as you know, ASCE 7 is on a 5-6 year cycle, maybe 7-year cycle. And then 2 years after that will be IBC. And then IBC goes another 2 years after that. The ground motion provisions usually don't change until the next ASCE 7 cycle. So 722, which is the next ASCE 7, that will have a major departure, this multi-period spectra and all of that. And that would be IBC 2024, perhaps, if IBC goes that direction. And then usually, at least for California, it will take another year after that to adopt. And then the particular jurisdictions may take another 6 months to a year to adopt. So for example, for California, it could be 2025, 2026 maybe. But for Washington, I'll leave it in my the good hands of my friend Patrick.
Yeah, so I guess overall, Bill, I mean, you know, the code cycles get more complicated and more fine-tuned as you go along. But in general terms, for the seismic portion or the ground motion portion, as Ramin mentioned, that is updated with the ASCE 7, which is about on a 5-year cycle. The International Building Code is on about a 3-year cycle. And then it does take about a year to 2 years to adopt at the state level or at the jurisdiction level. But overall, this code cycle, there is a very noticeable change in the seismic ground motions. We do expect it to be, well, this has been a lot more than we've seen in previous cycles. There is going to be a large change, as Ramin mentioned, with the multi-period response spectrum coming out, but we expect it to be relatively similar to the loads that we're seeing now. Ramin maybe can talk a little bit more about that in a future presentation, but yeah, as we go forward, it just tends to get more complicated and more specific.
Thank you.
Yeah, just to add, as I mentioned, the reason for the big changes in ASCE 716, and that kind of relates to the site-specific, which is Chapter 21 of ASCE 716. These big increases were kind of were because we were going to go to the multi-period and these basin effects and all of that. People knew about that, but ASCE 716 wasn't going to do a wholesale change. So that wholesale, although it is in there in kind of a roundabout way with these increased factors, but I agree with what Patrick said. I don't think we're going to have a big change, but the numbers may not be that different for most practical purposes as far as the 722 is concerned.
All right. Well, I think we will leave it at that. And thank you so much for the great presentation. Very, very informative. Ramin, Patrick, thank you. And we really appreciate all of it. Just a couple of announcements before we finish up. Thursday, September 29th is our Culture of Care Forum. October 14th, we'll have our federal facilities 3-year outlook. And on October 20th, we will get an update from Sound Transit on the future of their projects and funding, which should be fascinating. We hope to have everyone back for that. So thank you again and have a wonderful day.